G'day everyone, how you going? A bit of a video here on some differentiation. There's a previous video on differentiation by first principles, which is where this idea comes. Just see differentiation as I'm working out the gradient function. And then from that gradient function, I can work out the gradient of the curve at any particular point. I know that's a lot of words. It'll start to make a little more sense as you move further into this. So this idea here is like a generic formula. It's a polynomial raised to some power n. Okay? So from that there, if I was to take the derivative of that, then what I really do is I take the power and I move the power out front and I lower the power by 1. So here the power is out front and here is the power lowered by 1. That's what we're doing with differentiation, and we saw that through differentiation through first principles. And you could put any polynomial into that and you'd get this out, perhaps with numbers as well, if you did it with, you know, x squared or x cubed or something like that. Just be aware of different notations. They all mean the same thing. We generally say y dash, dy dx, or the derivative of y with respect to x, or f dash of x. They all mean the same thing. They all mean the same thing. Don't get worried by this. This is the key thing here, being able to differentiate polynomial functions. Here's an example. Y equals 4x cubed. So what am I going to do? I'm going to take the power out front and lower the power by 1. Now I did it this way. This 4 here, don't do anything with that. That's just a coefficient. Leave that exactly where it is. Just differentiate this part and you can see that that becomes this here, 3x squared. Power out the front, lower the power by 1, and then your normal algebra, 3 by 4 gets me 12. There's my gradient function, or the derivative of this function here. Okay, so that's what we're working with. Let's do a couple of examples here. Here we go, y. If it's set up like this, normally easier to use y dash. Don't have to. I'll do it differently down here just to show you the other notation. What are we doing? Power out front and lower the power by 1. So this is going to become 4 times 6x to the 5. And I could tidy that up and say, well, that's going to be 24x to the 5. That's all we need to worry about there. Very similar example to this. This is a little bit different. Okay, for two reasons. One is they've written it as f of x, the function of x. Absolutely fine with that, no issue whatsoever. We could just change it to y if we wanted to. And we've got 1 over x squared. Now I'm going to suggest that to do this one, the better thing is to rewrite that as x to the minus 2. Now these are exactly the same, but now it's in this format and I can use this idea. So now I'll say f dash of x equals power out front, so that's going to be minus 2, times x lower the power by 1 is going to be minus 3. Remember, lower the power by 1, minus 3 is 1 lower than minus 2. And if I wanted to, I could tidy this up to a similar format that I was given and say that's minus 2 over x cubed if I wanted to. Okay, so just follow this step here, that we're really putting it into a format that I can use. Differentiate, tidy up if you want to. The tidy up step isn't essential. Right, this one here. I want to recognise that the square root of x is the same as x to the half. Okay, square root means x to the half. The cubed root, if there was a 3 in here, would be x to the 1/3. Okay, don't get worried why that is for the moment. Let's just worry about our differentiation. Now I'm going to use other notation. I could use y dash, but I'm going to call this one dy dx. Now remember, they're exactly the same. Y dash, f dash x, dy dx, they mean the same thing, they're just different notation. That's all. So here we go. This is now in this format. So power out the front means I'm going to go a half, that's the power out the front, times this, but lower the power by 1. Well, if I lower a half by 1, I get negative a half. So I end up with this idea here, which I can tidy up to 1 over 2 x to the half, or 2 square root of x. Okay, so that's just a bit of a tidy up that I can do there to make that work. Very common sort of question. Any differentiation test that you do, it's going to have a few of these saying differentiate the following, off you go. This is the style that you need to do. They will also have questions where it says find the gradient at a particular point. All right, now there's a bit of information here we've got to be aware of. We've got our function. This is not dissimilar to here. We've got our function and we've got a point. That point links to that curve. That is a point on the curve. Okay? But what we want to do is we want to find the gradient at that point. The x value is the only thing that we want. Okay? The y value only links to the curve. The x value is the thing that we can put into the gradient function to get the value of the gradient. Let me do a quick little sketch here. This is a quadratic, so it's going to look something like this. It's going to be fairly shallow because it's 0.25, so that's sort of shallowing it out. At the point 4, well, I'm going to put 4 here. That point there is going to be 4. That's what the information is telling me. Now, what the question is asking is saying, at this particular point, right here, what is the gradient of the curve? Well, the gradient of the curve would be the line that just touches it at that point. And the question is saying, what is the gradient of this line? Well, the first thing I'm going to work out is the gradient function. And then once I've got the gradient function, I can substitute in 4 into that gradient function and get the value of the gradient at that point. So if I take the derivative here, y dash equals power out the front, so it's going to be 2 lots of 0.25 or 0.5 x. Power out the front, lower the power by 1. Now what I'm going to do is I'm going to substitute in that point there into there and get y dash to equal, multiply it, 2. So that means the gradient of this function at this point is equal to 2. What does that mean? Well, it means that this line here would have a rise of 2 and a run of 1, wouldn't it? Because gradient is rise over run. That makes sense? 2 over 1. So the gradient of this function at this point is equal to 2. Okay? Let's do the next one here. Now, I chose this one specifically because I don't want you to get confused about this. All right? Let me write this a different way. Instead of writing x squared over 5, I could write 1 over 5 times x squared. This is the only part that I need to differentiate. The 1 over 5, that's just like the 4 here. It's a number out front. It's just like the 4 here. It's a number out front. I just leave it. Leave it alone. Don't do anything with it. So differentiating this, power out the front, lower the power by 1. When I do f dash of x, this is going to become 2 over 5 times x, x to the 1 if you like, but I'm just going to write that all together as 2x over 5. Okay, so that's my derivative of this one here. Okay, now similar step to up here. Take this value, the x value, and put the x value into the function. Now a neat little way of using this notation is now I can write this. I can write f dash of 2. Right, so I'm saying what is the derivative, the value of the derivative when x equals 2? And that would be equal to 2 times x over 5. 2 times 2, 4, divided by 5, 4 over 5, or if you like, 0.8. So it allows me to, this notation allows me to put my x value in there, so it's a little clearer what I'm doing. This, it doesn't kind of allow you in the same way to do it, but it doesn't really matter. The information was right here anyway. You should have figured what you were going to put in.
Yeah.
Hopefully that one helps. It's just a few questions there on differentiating, and then differentiating to find an actual value for the gradient. Hope this video has worked. Thanks very much. See you later.